Okay, sorry, I wanted to get the thing set up. We've got.
So were the grades you posted on Carmen after you adjusted them?
Oh yes.
Okay.
Yeah.
We were all a little curious about
That was.
Yeah, in the announcement I mentioned the range of the raw scores.
You said there was no uniform score.
Well, yeah, so it was as if the grades were uniformly distributed between the high and the low. Like there wasn't like a bell curve for the class. It was like flat profile, right? So you pick any increment in between there. So
it's bizarre.
that's why it took so long for me to post the grades, because usually there's like a clear curve, or you end up with a graph that looks like a step, right? When you plot them, right? And so there's natural places to kind of break grades, and there wasn't. So I struggled with a whole bunch of different normalizations to try and, right? Because the one thing is there were several people who did really well with their raw score. And it's unfair to penalize those people negatively, right? So how do you come up with a fair, so it took a while. I ended up doing a z-score and then linearly scaling it on a range, so that it was only possible to go up. But I've got a huge stack of stuff. One other announcement, I have to travel for a program review Wednesday, so there won't be an in-class Wednesday. The other notes, there's the lectures on crystal plasticity are up. The next set of lectures, which will be on plasticity and amorphous materials, will be up, and then that'll be up probably Wednesday or Thursday. And then there's there'll be a couple weeks left, and there's kind of a range of topics that we can cover. So what I want to do is I'll set up like a survey, right? And I think we'll list 5 or 6 potential topics, and then you guys will pick 3. This class, there seems to be more than usual polymer and bio people in here. So I'd like to do some things on cellular materials and perhaps nonlinear viscoelastic, things that might be more of interest to a good chunk of the class. But we'll put up a survey and sort that out. So, okay. So, Nick is distance. So, let me pause this. Also, I didn't post the solutions because I wanted to spend some time today going over them. Based on
common failings.
Based on, there were some really common problems, which points to a failing to me, right? That there's something that obviously didn't quite get across, so we'll take this opportunity. Oh, and also the final is cumulative, right? So, all right, if you do better on the final, it basically can erase this grade. But I mean, the grades were, the distribution was
strange.
Well, yeah, but I mean the final. Okay, so the short answer. Everyone basically did just fine. When I was grading them, I scored them each as 1 out of 5, right? But that was just kind of like my internal bookkeeping, right? They were all scaled up accordingly. So if you are confused about why you lost points, let me know. I also, when I go through and grade this, I went through, I did all of the question 1s and then all of the question 2s, right? So it was.
That sounds painstaking.
Well, but it's, I want to be consistent about it, right? Because if you don't, if I read the whole exam through, your baseline of what you give points on for each question kinds of shifts. Okay, so question 1, almost everyone got that basically a second phase forms at 35%, right? And so you
Could you read what the question was, because we don't have the.
oh yeah, I'm sorry. So question was, said the yield strength of and tensile strength of copper increases with addition of zinc up to 35% zinc. Further addition of zinc causes an abrupt drop in strength, right? And that's basically you enter a two-phase region, you start precipitating out. The zinc, and depending on the nature of the particles, right, it could have a reduction in strengthening. Question 2, explain why the modulus of elasticity of BCC is higher in the 111 direction compared to the 100 direction. Basically, if you said, 111 is the close packed direction, right? So that's, right, that's the majority. A lot of people got confused and talked about plasticity there, talked about slip, about how the spacing of the 111 planes versus the spacing of the 100 planes, and that doesn't, for elasticity, that's not it. It's just you're pulling on bonds, right? So if you're pulling on a close packed direction, right, your force is, right, you're serially over the most bonds in that plane. Whereas if you're pulling along the 100, right, you've got, your bonds are farther apart, and so even though the strength of the individual bonds is the same, you've got less total force. Okay, so 3. Oh, I should turn this. I will need this for the long answers.
It's like a comedy routine.
Okay. Okay, so basically, if we've got a dislocation loop, right? This says speculate as to why the Berger's vector must be constant for screw edge and mix section of dislocation. Well, you didn't actually have to invoke screw edge or mix, right? It's just the notion of what is a dislocation, right? The dislocation is you can think of it as a boundary between the region that has slipped, right, and the region that is unslipped, right? And so if this is sheared here, right, it's all sheared by the same magnitude, right? If you have part of the crystal that's sheared by a greater magnitude, it means that you need something like this, right, where this would be a partial, this would split into partial, right? You would need something. But if this is the region between the slipped and unslipped region, right? It has to have the same, it has to be slipped by the same magnitude, which means that the Berger's vector needs to be constant across the whole loop. Okay, so neohookean, this was, I think, the one of the short answer that screwed up the most people. basically, right, what are the assumptions? The assumptions are a Gaussian distribution, right? Chain statistics, and that right, and that's really the that was the big thing that lots of people missed, right? It's a random walk. The chain statistics are Gaussian. We assume that the chain is freely jointed, right? And that there are no distinction between crosslinks, right? They all have the same effectiveness, right? And so what microstructural features are missing that contributes to its poor performance at larger strains is really the nature of the crosslinks, right? Not all links are equivalent, right? You have, in real chains, you have terminated ends, you have loops, you have temporary entanglements, right? Where you've got chains that pass through each other like this that aren't really crosslinks. And so that's the microstructural features, right, that are missing, that why neohookean breaks down. 5 Y1111 right, is the observed slip system instead of 100110, right? And I think basically everyone got this, right, that attempted it. Right? If you think about what goes into the piral stress, right? The Berger's vector is shorter, right? The plane spacing is larger, right? So these dislocations can move, right? Whereas these ones are sessile, right? Under extreme conditions, very high temperatures and basically shock loading type conditions, extremely high deformation rates, you can get cube slip, 100 slip in FCC metals. Right? Doesn't happen easily, but it can happen. Compliance curve. A couple people plotted the relaxation curve rather than compliance. So this is T, this is J. So we've got glassy, viscoelastic, rubbery, and viscous flow. And if we change the temperature, if we increase the temperature, this curve will shift that way, Higher temperature means that viscous flow happens easier, and then 7 on the short answer did throw some people for a loop, not because they didn't understand they just got the definition of kink and jog reversed, right? So a kink is a special type of jog, right? A jog usually goes across planes, across slip planes, right? It takes you out of the plane, and I'm going to try and draw this in a horrible way, right? So you've got, if this is, let's draw one plane, right, and then another plane, right? And a jog basically is out of the plane, whereas a kink, is in the slip plane, right? And this is kinking is how dislocations move, right? Because you've got your Peierls Nabarro barrier, you have to overcome your Peierl stress, which if you do that for the entire dislocation line is hard, right? But I can move this part forward a little bit, And now my whole dislocation can move forward by this kink, simply spreading, right, laterally, right? And that's a lower energy cost than moving the entire dislocation line forward, right? Because you have, you're only moving this length here, right? And your penalty is the line tension to cause this, right? The line tension is going to be related to the dislocation. The width, right, of your dislocation core. And whereas if you're moving a big chunk of the dislocation, right, you're moving this whole region, right? But you don't have the penalty to pay for the curvature, for the line tension. But that was really it, right? I mean, everyone basically answered the questions pretty succinctly, so I didn't have to read a whole lot, which was good. And you can hopefully see, for those of you that tended to be a little bit more verbose, right? I'm really looking for very short, yes, I understand this kind of statements. Right? It doesn't have to be super deep. Okay, so the long answers. So these appeared to take people a lot longer than I anticipated. Hopefully, and a lot of people did what I think is a lot of extra work. So this is really why I wanted to go through these today, is to show kind of what I'm thinking about this. Okay, so question 1, right, is the cheese question, right? And
favorite of Dr. Anderson's.
yeah, I didn't know that. I thought I was being witty and clever. Right? So you've got something that looks like this. Right? This is time. This is strain times 10 to the minus 2 or 10 to the 2. Whatever the exponent is, it doesn't matter. So I said the first question is, how good of an approximation would linear viscoelastic be? Okay, so a lot of people went through and used one of the models, right, and then fit fit like the standard linear model or the Maxwell or the Voigt to it, right? So the standard linear model would be okay, but that's a lot of work to fit that, right? Just remember, what's the definition of linear viscoelasticity, right? Is that we have a time-dependent strain, a time-dependent creep modulus, right? And that our creep modulus is not a function of stress, right? So that means we can look at pick a constant time, right? This is at stress is, and this is 2.85 kPa. So we can pick 2 different stress values and 2 strain values at constant time, right? So here we have at 2.04, we'll use 20, right? And at 2.85, right? And that's just basically as close as we can kind of read it off the graph easily, right? And if we then take this ratio, right? If it's perfectly linear viscoelastic, this should be true, right? And it's not. We plug in numbers. Basically, we get 15 over 12 is I won't use the equal sign here because this will cause confusion. Our ratio is 2.85 over 2.09. So we end up with 1.25 to 1.39, right? And since we don't know which is the base, right? So we can just do a standard error calculation, right? 1.39 minus 1.25, 1/2, 1.39 minus 1.25, and that gives us about a 10% error, right, at this particular strain value, right? If you picked a different time, you would have a different error, but right, intuitively, it's a pretty simple plot, or a pretty simple calculation. Okay, so assuming linear viscoelasticity, suppose the 4.9 Newton load from the first experiment was removed at 100 minutes, excuse me, and the strain was monitored during recovery. All right, make the sketch. How long does it take to return to 95 centimeters of so there's a couple different ways you could go about this. Most people, and they got most points for this, right, basically made a quick sketch, right, and did it kind of approximate, and did something like this, right, and basically traced this curve and then traced this curve upside down, right, which, again, the only problem, the big problem that everyone who did this approach made forgot one thing, right? And it's Boltzmann, the Boltzmann superposition, right? So this part still keeps happening in an imaginary, and they also, oops, right? This part keeps happening on and on forever, and they forgot the initial instantaneous elastic response, right? So, right, but if you made a sketch like this, right, you would have gotten almost all the points, right, to show that the understanding there is the most important. But we can get quantitative from the graph, right?
Good.
And so basically if we've got time and strain, we get 3 and 7, 6 and 9, right, and down 120 and 24 times 10 to the minus 2. I don't know, I can't, the exponent is, I assume it looks like 10 to the minus 2 from the graph. I don't remember what it is from the actual method. Okay, so you could have done what we did in the homework, right? Except the homework problem the graph went on for more time than you needed, right? It went out for 3 hours, and you only needed 2 hours worth of data or something like that, right? So for this, you needed some way to continue this curve, right? So you could have done a simple linear extrapolation, right? The data points look like they're growing linearly, right? But that's physically, if we're assuming it's linear viscoelasticity, right, that is physically impossible, right? There were a lot of people actually that wrote linear viscoelasticity means this curve becomes linear, right? That's not true, right? The linear viscoelasticity means it behaves as a linear function. If this curve actually becomes linear like this and keeps increasing with constant slope forever, right, it's not viscoelastic at all, right, because it's not recoverable, right? No matter what I do, I will always have a permanent plastic offset, right? If I were to drop this down, right, and start decreasing with the same curve, right,
I would decrease, but then once I'm asymptotically in the region where the slope is constant, I would just go out at a plastic, right? Because I would have the same slope. So this needs to decay, right? So that means you need to either assume that it decays in some way, or think of a really simple functional form. And this is where I think that I overestimated I don't know, that sounds bad. I overestimated your intelligence. No, that's not what I'm saying. Right. I think it's just an experience thing, because I looked at this and said, okay, so the let's pick a simple power law, right? That's going to work really well for this, and so the standard power law form is going to be A T to the B plus C equals epsilon, right? Because we have this is the elastic offset, so we can read this just from the graph, right? That's the C is the initial jump, right? A T to the B, for these sorts of things, what's always a good guess for B if you don't know, if it's a decaying, right? Something less than 1 but greater than 0, right? So I just said A square root T plus C equals epsilon, right? And again, this is just pick, and then, right? And so that means the only thing you actually have to fit is A, right? And it turns out that 2 square root of T plus 4 gives you when I checked it in MATLAB for an R squared value, right? So I went through and actually digitized this plot and then fit the data, and if you just plug this in, this gives you an R squared value of like 0.98. Right, so I just kind of, this was me over assuming, right? I just thought everyone was familiar enough with power laws and curve fitting that most people would naturally assume. It looks like a square root dependence. This is the offset. We only have one number to fit. You don't actually have to do a curve fit, right? You don't need to do least squares. You could just roughly see what it was. So this is.
That's where a lot of us do not have to work.
This is. No.
I tried to curve fit it, and my inspection of a graph was crappy, so I was.
Some people did do curve fit. Again, the curve fit doesn't matter, right? As long as you have something that decays, you didn't even have to fit it. You could just have written, right, it's linear viscoelastic, so it has to decay, right? We're just going to assume that it decays to 0 at 200 minutes or something like that, right? And that would have been more than enough. Or you could have sketched the graph with the appropriate drop, right, and the superposition. And that would have been more than enough. So basically we have, so for time less than 100, we've got this functional form, 2 square root T plus 4. For T greater than 100, we have our epsilon is equal to 2 square root of T plus 4 plus, oops, that should be minus 2 square root of T minus 100 plus 4. This is to the, yeah. Right? Like that. And so the 4s go away, right? And yeah, basically, right, then you can just plot your curve, right? You got something like this, right? And then you've got something like this, right? This keeps going, right? And then you can plot your curve in between here. Right, so you, even without doing the curve fit, you could have gotten almost all the points on that just by saying Boltzmann, right? It's going to look like this. This is what the graph is going to look like, right? That to me is a lot more important than the actual numbers. Question 2.
So what was the actual time?
Oh, I got
Just out of curiosity.
425 minutes. Right? So, a good chunk of hours. 2, this problem I thought would be super easy. But again, a lot of people had problems. So I said you've got the 0.22 weight percent carbon, right? And we assume that it all comes out of solution. I can't believe, who has the exam? I lost the copy. A lot of people turned in the exam. I still have it. I just want the wording to be right. Just the second question. Oh. Yeah, okay. Right, so I said the maximum solubility of carbon in ferrite is 0.22 at 727 C, right? So we assume that we can all retain it in solid solution during a quench to room temperature, and then it becomes precipitated at Fe3C, right? So not really a physical process, but an idealized kind of process. Okay, so what volume fraction precipitate would be formed, right? Neglect any difference between. So I thought everyone was doing everyone had thermo and everyone had diffusion and kinetics. So I thought this was kind of like a gimme couple points because it was something that everyone did recently, right? So if we assume that we had 100% Fe3C, right? All right, iron is 55.85, 12.0, right, is the molecular weight of carbon, right? So that gives us a molar mass of FeC3 of 179.5, right? Grams per mole, right? And so if we have one carbon divided by 179.55, that gives us that FeC3 is 6.67 weight percent carbon in pure FeC3. Then how do we determine the fraction if it all precipitates out, right? The fraction of FeC3.
I just figured out the total number of moles of iron and carbon.
Wait, let him get to the punchline first.
We have, right,
Yeah.
it's a lever rule problem,
Yeah.
right? It's a binary phase diagram, right?
Oh.
Right? So it's just XA is C minus B over A minus B, right? And since there's nothing left, right, it's line compounds at the end, it just becomes 0.22 minus 0 over 6.67 minus 0, or 0.32%. Weight percent FeC3, Fe3C, right? Right. So I thought that was a complete and total give me, right? And
Did you ask for weight percent or mole percent?
He gave us everything in weight percent.
I gave it on weight percent,
So-
right? But then I said neglecting any difference between the densities of Fe3C, right? So I made it even simpler and said you don't have to convert between atomic fraction and weight fraction. Right? Just use them interchangeably. Okay, so estimate the increase in yield strength. Okay, so what do we need, right? Basically, the increase in yield strength is going to be right? So we know the radius because it precipitates out as 50 nanometer particles. We just need to calculate what the spacing is. I give you the shear modulus and I give you the atomic diameter, right? So you have good approximation for B. I give you, yeah. So basically you can think of, you make a cube, right? This is L, approximately L, right? The particles are small, right? So really this is technically L minus 2R. Right? This is R. But if you just assume this is L, your error is like 1% or something like that. And so the volume of the cube is 4/3 pi r cubed as the volume of the sphere. The volume of the cube is x cubed, right? And if you assume 50 nanometer particles, right, this becomes like the volume of the particle is 5 times 10 to the minus 22 cubic meters, right? And then you need to figure out, you know the volume fraction of the particle, right? You calculated that in the last problem. So you just need to find the L that gives you the right volume fraction, right? And this would be assuming a uniform, that the particles are uniformly on a uniform grid, basically. But for the average, that's going to be pretty good. And it works out to be, L is about 55 microns, right, is the particle spacing, right? So if you plug all that into here, you get 2 GPa, right? This assumes that no cutting, right? This is the equation to bow it out, right? 50 nanometer particles, right? They're small, right? So you can assume, if you assume that there's cutting, you can go through the calculate the shear strength and the APB energy, right? But this is a lot more straightforward if we just assume that we're going to be bowing around them, right? Then this is high. This is a little high, right? So you can say, yeah, this is high. So it's probably, we're probably going to cut, right? But if you went anywhere close to this far, I would have been super happy, right? So the other part then is how much of a loss did you get from solid solution strengthening, right? And basically, in the notes, slide 25 in the lecture, there's a graph, delta sigma square root of carbon content for iron, right? And then you can just read off that graph, and it was 400 MPa, right? So that's what you lost from solid solution strengthening, right? You also could have calculated it out, right? It's a tetragonal distortion, right? Because it's interstitial in BCC. So there's an equation for that. And you could have figured out your A value, your alpha value out front of that. I gave a range. It was like 30 or something, 30 to 200. All right, so if you picked that and plugged it in, you could have gotten a value that was the same. the same as well, right? But the only difficult part of the whole thing was you had to make an assumption about whether cutting or bowing was happening, right? And then you had to figure out what your particle spacing was. And then the last one. This one, I have to say I was disappointed in. And it means that I did not get a really important key point across. So I gave a admittedly flawed compliance matrix, right? So I'm not going to be quantitative in my solution. I'll just show the equations and just leave it symbolic. But, right, and I said we have two cases like this, right? This is 5 degrees, right? We have a non-compliant piece of wood, right? And the first question is calculate the Young's modulus. No, so obviously everyone realized that we need to form the transformation matrix, right? We can treat this as a 2D problem, right? So our transformation matrix is cos theta, sine theta, minus sine theta, cosine theta. Doesn't matter whether this is a positive or negative deviation, right? The symmetry of the system, it doesn't matter. Right, and theta here is 5 degrees, so it's pretty small. Cos theta is pretty close to 1, 0.996, 0.087, right? 0.996, right? You could use the small angle identity and just plug in, right? Or you could just plug into your calculator. Okay, so what's the formulaic way to compute the Young's modulus, right? And here's where I think everyone went completely off the rails. In the form that it's given, right, I give S as a 6x6 matrix. Because it's basically a 2D problem, you can reduce this down, right? But if you do this, is this 6x6 matrix a tensor? No. It's a way of representing a fourth order tensor as a matrix, right? So can you transform S as the matrix? So basically everyone went S prime equals QSQ transpose, right? And this is not true, right, in any way, shape, or form, right? How does a fourth order tensor transform? If you were to go about doing it this way, right? We know that Young's modulus is 1 over S1111. So we could transform S to find the Young's modulus in the new frame, right? So that becomes Sijkl prime equals Qi R QJS QKT QLU SRSTU. Right? And you could solve this out for S prime 1111, Q1R, Q1S, QKT, QLU, SRSTU. And if you had MATLAB open or you were really good with your calculator, right, you could do this calculation pretty, right? It's a lot to do out by hand, but you could have done it using the the tools you had with you at the exam. Part C, I basically said there's a much faster way of doing this than transforming the compliance tensor. But no one saw the fast way. Basically, what we did here. You can either transform the stiffness, or you can do the stress and strain calculations, and then transform your result. Right? So, I'm a little frustrated with myself that somehow that didn't quite get across, because there wasn't a single person who actually got this question. I had to dig deep for points on this question. Right, which in my mind says there was a disconnect between the mathematics you did and the application, right? There was something there that we need to work on. So, okay, well, we're a couple minutes over, so we'll stop there. There's no in-class on Wednesday. Monday, we are going to go through homework questions for the crystal plasticity homework that's been posted. Right? So, especially the Bishop Hill analysis. Right? That one is always confusing for